Hi everyone, welcome back. Long time no see. Today we're looking at the A-star algorithm. So let's get into it. So what do we need to know about A-star? Let's start by looking at the study design. Our Unit 4 Outcome 2, and our key knowledge for that, says that we need to know the hill climbing on heuristic functions, the A-star algorithm, and the simulated annealing algorithm. I know that just one little dot point, we just need to know the A-star algorithm. It's a bit vague. And then our key skills, and you might be reading these and thinking, what does that have to do with A-star? That we've got develop different algorithms for solving the same problem using different algorithm design patterns and compare their suitability for a particular application. We've also got apply heuristic methods to design algorithms to solve computationally hard problems. So the reason these are related is that the A-star algorithm is a heuristic algorithm, which we'll get to in a minute. And a lot of the application we need for this algorithm is just kind of understanding how it works and also understanding how it can be better or worse for the same problem. Most of the time it's going to be better for the same problem than other existing algorithms. And this might come up on the exam, however, it might be more relevant to your SATs than a SAC or exam because it's more about the application of it than questions of it. And it didn't show up on the 2021 or 2022 exam, but it did show up on the 2023 exam. So we'll have a look at that question at the end. So, heuristics. A heuristic algorithm tries to make a good guess at a solution quickly. So that's all that it really is. It's just a good guess. Now, it's not a bad guess, it's a good guess. But it doesn't guarantee the best solution. A good solution, but not the best solution. Sometimes it does guarantee the best solution. In one of those cases, we have A-star does guarantee the best solution. So, how do we make sure it's a good guess and not a bad guess? So we use heuristics. That's a random method maybe, a greedy method, like Dijkstra uses a greedy method. We might use statistics, or we might use prior knowledge. Now in our case, we do actually use prior knowledge. A-star uses prior knowledge. We'll have a look at what that means in a minute. A-star uses a heuristic, h of n, which is the estimate to the distance of the goal node. So that's our heuristic that we're using, and that does involve prior knowledge because we need to know the distance to the goal node from other nodes, or from the start, and we can calculate that along the way. But we need to know the distance to the goal node. So that's the main prior knowledge that we're working off of here. Let's get a bit more specific with that. So A-star is similar to Dijkstra, but the cost is based on g of n, which is the same greedy cost to the current node that Dijkstra uses. So on our little image here, we've got that red line is our g of n. That's our current cost that we've got to the current node. And then we've got h of n, which is the heuristic value between the current node and the end node. So it uses both of these to form f of n, which is our total cost. So h of n is that green line, and h of n can be measured in a lot of different ways. It depends on what prior knowledge we have. Sometimes it might be coordinates of some kind. It could be maybe the Euclidean or Manhattan distance. A lot of examples might use a maze because then we might be able to form a grid pattern, and that might use some kind of coordinates or Manhattan distance. But we'll have a look at some questions and be able to understand that maybe a little bit better. So let's have a look at what the algorithm looks like. So comparing A-star to Dijkstra's algorithm in plain English. Now this Dijkstra's algorithm in plain English you can find on the LMS. The A-star one I've just edited Dijkstra's to have, and you can go to the LMS to look at the structured pseudocode for each. We're using the plain English version because it's going to be a little easier to understand for this task, and you probably aren't going to need the actual structured pseudocode for your exam, but you might need it for some kind of SAT. But for now, we're just going to look at the plain English because our main goal here is understanding how it works. So where the sections are the same, we've highlighted them. So for our first highlighted section, all we're doing is just going through all of our vertices and listing them as unvisited and initializing their starting distance to 0 for our starting node and then infinity for all the other nodes. Now A-star does something extra here where it sets the vertices to an estimated distance of h of n to the goal. So this distance here is going to be from all the nodes to the end node for our goal node, and that's our prior understanding. So we need to figure out how that's measured, but for now that's all we need to know is that it's setting all the vertices with that estimate, and then we can therefore calculate f of n based on that. Okay, our next task is a big while loop, and this is going through all of the unvisited vertices. So our first task is to pop vertice v off of our priority queue, and that's going to be the total cost of f of n for our A star, or just the distance, the smallest distance for Dijkstra's. So this is the big difference here. This is probably the biggest difference on the whole thing, is that instead of just comparing the straight distance from the start to the current node, we're actually comparing the total cost of this node being taken. And then A star does something here where it checks if we're at the goal vertice or the goal vertex, and if we are, then that's great, we can finish here. If we're not, then... So Dijkstra doesn't do this. Dijkstra doesn't check this at all. The reason is because Dijkstra is actually finding from one node to every other node, which is one of the things that makes it a bit slower than A star, but that's because it's not really a pathfinding algorithm, like something like A star or breadth first search or depth first search, which is the other things you might compare A star to, would do. So A star is just trying to find a goal rather than the path to every other path. So they do have a slightly different requirement in that sense. So our next thing that we're doing is this for loop, and that is finding all of the neighbors of vertex v and checking the distance of them to see if it's greater than the distance we have saved already. And if it is, then what we're doing is just updating that distance, and then the extra thing A star does is recalculating f of n. So it's really, really simple. It's not that different from a Dijkstra's. It's only a couple lines different, and some of the lines that are different you'd be doing in breadth first search and depth first search anyway. The main thing is that it's using a priority queue with f of n, whereas Dijkstra's using a priority queue with just the distance, and then something like breadth first search and depth first search might use just a queue or a stack. So that's really all it's doing. It's just how it's deciding which node to go to next is the main difference. And yeah, you might find here that's the priority queue, f of n. So let's have a trace. Let's have a trace of A star. So this might be my mouse maze, and I've labeled all of my nodes here, which is our squares on this grid, and we can imagine these black lines to be the walls of our maze. So we've got start and end, and I know where end is in terms of the coordinates, and therefore I can figure out how far each square is from end, and I'm going to be using the Manhattan distance for that. So starting at start, our next node is going to be A2, that's all we can go anyway, so we'll go down there, and to figure out for A2, we know that A2 is going to have a distance from start of 1, so that's going to be our G of n. And then our h of n is 3, because we can go across 2 and then down 1 to end. That's how we can get to end. So that's 3 squares apart in Manhattan distance. And then our f of n is therefore 1 plus 3, which is 4. I'm not going to calculate that every time, but you should be able to see how that works. So then our next is going to be B2. Again, that's the only node we can go to. That's going to have an f of n of 4 as well. So 2 away from the start and then 2 to end. And then next, we could go to B1 or we could go to B3, but we'll go to B3 because that's closer to our end. It's only got an h of n of 1. So we'll go down to B3. Okay, now that we're at B3, we've realized it isn't actually 1 apart because there's a wall in the way. That's something that A star does. We don't actually know how these nodes are connected, but we do know relatively where the end is. It's optimistic in that sense. It goes towards it even if it's not the best way. So that's what we've done here. So what we'll do next, now that we know there's not a wall there, we'll figure out what we want to do next. Let's go back, let's clear our priority queue. Let's have a look now. So we can go to B1 or we can go to B4. Now both of these have an f of n of 6. B1 because it's 3 away from our start and it's 3 to the end, has 6, and then B4 is closer to the end but it's further away from the start, so it has 6 anyway. So just because B1 is the top of our queue, we'll go there, and then we can go to B4. And then we can add their descendants to our priority queue. So we've got C1 and C4 are both equally good options. They're both pretty close to our starting node, and they're both pretty close to the end node. C4 is obviously a bit closer to the end node, but we'll go with C1 because it's the start of our priority queue. And that's going to have 6. We go to C4 as well, so we'll go to both of those. And then we'll go to A4, because that's our next option in our priority queue. So that is at f of n of 8. So we've got 5 from the start and 3 from the end. And then we've also got A3 on here. And we've come to a dead end. So we can refresh this and look where we're going now. We've cleared all of our dead ends for now. And we can go back to C4. And from C4, we've only got one option. We'll go forward to D4. And then from D4, we can go to D3. And then from D3, we can go to D2. Now, here's what we do interesting, is that we are not going to explore D1 at all. And the reason for this is because it is really far away from the start, and it's also not very close to the end relative to all of our other options. So we're just not going to explore that at all. We'll go to C2, and then we found our end. So that's our trace of A star. I know it's not that dramatic when I'm doing it one at a time, which is why I've got a beautiful visualization for you. Now this visualization shows two cities, Chicago and Rome, and it's showing A star from one location to another location using all of the different path options. And it's quite beautiful, so I'll let you enjoy that for a minute. Okay, I hope you've enjoyed it. Now let's look at some practice questions. So this is the only practice question we have, and this is from the 2023 exam. And let's have a look at this question. So Sam is creating a maze-solving program that takes a satellite photo of a maze as an input and returns the path from its entrance to the center as an output. So the center is our end. Image recognition will be used to identify features of the maze, such as its walls, entrance, and center. What algorithm is likely to be most efficient for Sam to use to find the path from the maze's entrance to its center? So let's have a think about this question. We're looking for an efficient algorithm, and we have some prior knowledge here. We know where the center is. So if we think about breadth first search and depth first search, they're not very efficient, and they don't know where the center is regardless. So they're not going to be that efficient for this question because we have that information. Something like Dijkstra's algorithm would maybe be quite efficient, but because we have that information, I would say that A star is going to be our best option here because we know where the end goal is. So I would choose A star, and that's your answer. We don't have the examiner's report yet, so I hope that I answered that one correctly. You can verify that once it comes out when you're watching this. But that's our practice question. So I'm not going to guarantee it'll be on the 2024 exam. I won't guarantee it's not going to be on the exam either, but you might expect a question like this where if we think back to that key knowledge, it is going to be something comparing to other algorithms is probably what we're going to see it come up as. And the algorithms comparable to A star is Dijkstra's, depth first search, and breadth first search. Okay, so that's what we've looked at today. We've understood what A star is, we've looked at what it means heuristically, and we've had a bit of a trace of it, and we've looked at that not quite pseudocode, but almost pseudocode for it. So if you've got any more questions, I'd have a look at the LMS and actually read that proper pseudocode for it, and I'd love for you to talk to your teacher and your tutors about it. But otherwise, you can restart the video, you can do anything you want. Have a great day.